Look at these three words, cat, dog, and car. You instantly know that cat and dog are more closely related. But how can an AI system tell that the word cat is more related to dog than to car? AI does not begin with human meanings, it begins with numbers. So, before a language model can compare words like these, it needs a numerical representation of them, a vector, an ordered list of numbers. In this video, we will build that idea from a single arrow to the kind of representation used inside AI. This is Theory to Binary. Today, let's look at why AI represent words as vectors. So what exactly is a vector? Let's start with these two numbers, 3 and 2. On a coordinate plane, they tell us to move 3 steps to the right and then take 2 steps up. Now draw an arrow from where we started to where we ended and we get a visual picture of the vector. But the arrow is only one way to show it. The vector itself is simply an ordered list of numbers. Now, depending on the situation, those numbers might describe movement, a position, or even the features of something. Now, let's take an example of a toy semantic space. Here, the axes represent animal-like and commonly kept as a pet. Dog and cat appears close together because they share similar features. Tiger is still animal-like but less commonly kept as a pet, so it appears lower down. Car, on the other hand, is very different, so it appears much farther away. The short distance between a cat and dog suggests a strong relationship, while the longer distance from cat to car suggests a weaker one. Of course, this is only a 2D example. Real embeddings use many more dimensions. But real embeddings go far beyond 2 dimensions. Instead of only 2 numbers, a word can be represented by a much longer list containing hundreds or thousands of values. We cannot draw all those dimensions, but a computer can. So how a word gets its vector? First, the text is broken into tokens. Then each token is matched with a row in an embedding lookup table. Here, the token cat selects the cat row. The number in that row becomes its initial embedding the vector model starts with. But this initial embedding is only the starting point. The meaning becomes clearer once the model sees the surrounding words. Take the word bank. In riverbank, the context pushes its vector towards the meaning of a land besides a river. In the savings bank, the same starting vector moves towards a financial meaning. Same word, same initial embeddings, but different context creates a different result. So why represent information as vectors? Because now AI can work with it mathematically. It can compare vectors, combine them, and it can transform them as they move through the model. Here cat and dog are at a closer distance while car is much farther away. But distance is not the only option. We can also compare the directions of two vectors. That leads us to the tools like dot product and cosine similarity. So now the question arises, how does AI actually calculate similarity? An image can be converted into a vector and compared with other image vectors, helping a system retrieve visually related images. A user's interest can also be represented as a vector. A recommendation system can then compare it with available content and suggest relevant items. The same works for documents. A question becomes a vector and the system searches for passages with similar meaning even when they use different words. So the overall process is simple. Information becomes a vector, the vectors are compared and transformed, and then the system produces an output. A vector then is a numerical representation that preserves useful relationships. We have seen this with words, positions, and directions. But the same idea can represent images, documents, user interest, and much more. In the next video, we will see how the dot product turns the relationship between two vectors into a similarity score. Curious how AI and modern technology work behind the scenes? Subscribe to Theory to Binary and follow for more.